Hello, guys. Today we are going to talk about an important concept in differential geometry, and it's called the fiber bundles. And it serves like a typical prototype for any other bundles that you can have, like tangent bundle, vector bundles, and so on and so forth. Okay. So here's the definition of the fiber bundles. E is the total space. B is like the base space. And then pi is the projection, bundle projection operators. And then F is the fiber. E, B, F, they are all smooth manifolds. And the the bundle projection function is a surjective map onto the base. Now this is one way to write the bundle is just by this statement right here. Okay. Or you can write it in parentheses like these four objects up here. Okay, now for any p, pick any point on the base manifold B. Okay, there should be some open set U or some neighborhood containing P. Let's call it U, and U is a subset, of course, a subset of the base manifold. Okay, so it's itself a manifold. And we also going to need a diffeomorphism or homomorphism or homeomorphism, depending on the nature, the structure of the total space and the fibers. But basically, the diffeomorphism in this case is gonna map a inverse bundle projection of the open set U into the Cartesian products of U and its fiber F. So here U, I'm just going to write down U is a subset of the base manifold and P contained in U. So U is a neighborhood of P. Okay. Okay, so that's the diffeomorphism. It's going to split the inverse projection of U into the Cartesian products of U and the fiber. And then, of course, if you take the projection one operators, which is projection to the onto the first factor, then you get U back. So anytime you have this diagram commute, so for example, if you see the bundle projection pi going from up here to down here is equal to phi composite PR1. Whenever you have that, it just means that you have a local trivialization of your bundle. Okay. So here's another way to illustrate this. Okay. So the dimension of B, the base manifold, is n, but just for now, I'm just going to write it as one dimension. But keep in mind that that is an n-dimensional object. And then this square here, indicating that it's a total space. And then the pi here is the bundle projection from the total space E onto B. And what I have here on P here is pi inverse of P. We'll give you this line here. And then on that line, there should be some element called E. Okay. So E is an element of pi inverse of P. And then if you take the inverse pi of the open interval U of B, then you're gonna get that portion that I'm going to write in blue here. So that is going to be pi inverse of U. Okay. So it's a little bit larger than pi inverse of P. Okay. So again, E here is a total space. Total space means that it's contained the domain and the range at the same time. Okay. And then B, you could think of B the base space or the domain space, if you like. And then let W is some open subset in the neighborhood of E in the total space. So W here is a subset of pi inverse of U. So I'm going to change color here. I'm going to write. And then here is my homomorphism from the total space onto the Cartesian products between U and the fiber. So F here is a fiber. It could be vector uh, space. It could be complex vector space. It could be anything. Okay, and then of course you have the projection one operator back to the first factor. So as you can see, this is the same diagram I drew earlier, except it contained more information so that you can see more detailed structure of the thing. And of course, there's a projection two, which map these onto the second factor, so it map out the fiber F here on the right hand side. And then of course you have the W, containing E inside your total space. So right now, the homomorphism here is a mapping between W, which contain E, into the U Cartesian products F, and of course it's a diffeomorphism or homomorphism, depending on the nature of the chart. And then of course that's the section between the base space and the total space will cross over that element E, and whenever you have sigma of E of P, then that's going to be equal to E. Okay. So this is kind of like what you see here is the graph of the section on the total space. Called section such that the bundle projection composite with the section will give you the identity over B. So sigma of P is equal to E. Okay. Now we're gonna have the chart on the, let's see, the chart on the manifold, base manifold B, and the fiber. So there's two charts here. Okay. The first chart is going to be on the base manifold, and then the second chart is going to be for the fiber manifold. So in order for you to have a chart, you need to have some open subset in that region where you're mapping the object from. So here you have U is a subset of M. I mean, it's a subset of B, which is the base manifold. And let's call C1 is the chart. And then another open set V in the fiber F. and side 2 would be the chart going from F to their respective space. And by the way, the dimensions of the base manifold is n, and the dimension of the fiber manifold is n. I mean is m. Okay. So together, these two charts will induce a chart on the total space E. All right. So first, we have to get some results from topology. So this is just a little theorem, and the title of this is maps into the products. All right, so we're gonna let f is a function that maps some element, some region A into x Cartesian y, and it's defined by this: f of a, and a is in capital A, is equal to f1 of a, f2 of a. So think of this as kind of like a parameterized curve into two-dimensional surface, if you like. And we need to show that in this case, the f itself is continuous only if and only if f1 and f2 are both continuous functions. So you have to show both ways. Okay. And yeah, so CTS mean continuous. All right, so here's the proof. So let's go. Let's assume that f is. Oh yeah, first let's think of f1 and f2 are the coordinate functions for the function f. Okay. All right, so here's to start the proof. We're going to let pi 1 be a projection operator of the Cartesian products between x and y into x. So it basically maps into the first factor. And likewise, pi 2 is going to map the products into the second factor. And we know that pi 1 and pi 2, they are both continuous functions. So here, so that means if pi 1 is continuous, that means pi 1 inverse of some open set U subset of X uh, should be open. So there's some elements in here, and that would be element A. And also for pi inverse 2 of V, it's going to be equal to X Cartesian products V, which is a subset of Y. So these are both continuous functions because pi 1 and pi 2 are continuous functions. Now for each element A in the region A, we're gonna let f1 of A is equal to the projection map pi 1 of f of A It basically maps the first factor into, well, that's exactly what it is right there, okay? And f2 of a is equal to pi 2 of f of a. But since we know that the composite of continuous functions of f and pi 1 and pi 2 are continuous function again, so that means f1 and f2, they are both continuous function. So that's proving one way, okay? So you can see here that the f function of a is continuous and is composite with pi 1. Pi 1 is also continuous, so therefore fa has to be continuous function. And this theorem is very important for us to prove the induced coordinates on the tangent bundles. That's what we will ultimately get to, but we need this first. Okay? So now we just proved that f1 and f2 are continuous. So conversely, we have to go the other way. We have to assume that f1 and f2 are continuous function to begin with. Then we need to show that the function f is also continuous. Okay. And if you could do that, then you prove the theorems. But we need to show the basis of elements of these objects only. So, for example, um, let's just take U cross V, for example. It's a subset of X Cartesian product Y, and it's open. It's inverse. You take the inverse of the elements products right there. The inverse is open in A. So the inverse of the basis element U cross V So yeah, so if the inverse is going to be continuous, then it has to be open in A. Okay, so A has to be an element of the inverse function of the basis element. If and only if f of A is an element of U cross V. So that mean f1 would have to be an element of U, and f2 would have to be an element of V. All right, so here it is again, the inverse function of the basis element U cross V can be rewritten as f1 inverse of U intersection with f1 in f2 inverse of V. This can easily be shown. Okay. So we know that f1 is continuous function and f2 is also continuous function. The intersection is also continuous, so therefore it has to be open. If the right hand side is open, that means the left hand side is also open. So therefore, we prove the theorems that f is continuous. All right, see you in the next video. Oh, yeah. So we're gonna use this to get the induced chart in the generic fiber bundles, and then as an application to that, we're gonna show the induced coordinates for the tangent bundle, which is the point and the point and the velocity components. So it would be useful just to brush up on your topology. That would be very helpful. All right, see you guys on the next video.